The first classification modeling method we're going to look at is what is called k-nearest neighbors. And so just a reminder from our previous video, we would use k-nearest neighbors if we have missing data, because k-nearest neighbors and naive Bayes work best with missing data. We would also use k-nearest neighbors if we want to visualize the labeling and we only have two variables we're using to predict the label. If we also have, or if we have considerable overlap between our variables, then we would also find that we would prefer to use the k-nearest neighbors. So when we're talking about overlap, we're talking about if we had, for example, two groups, here's this blue group and here's this green group. The more those blue and green mix together, the more overlap, the harder it is to put them into one group versus another. And so the k-nearest neighbors performs better when there is that integration than the other models. Some of these other models don't work well if there's not this clear separation. The k-nearest neighbors, as we said, also allows for visualization. So if you have two predictor models, like on this graph, we have something on the x-axis, something on the y-axis. These are the two variables we're using to predict whether it is blue or green. And so the k-nearest neighbors allows for a visualization. Now, what do we mean by k-nearest neighbors? So we would choose how many nearest neighbors, so what is k, when we do this model. So here we have, here's our data here. The red one, we don't know which group it belongs to, so that's the one we're trying to predict. But first we're building a model based on our labeled data, our blue and our green. Well, if you have three nearest neighbors, if your k equals 3, then to find out what this red one is, we would look at the three nearest neighbors, and you can see that it is 2 green, 1 blue. So we would classify this red dot then as green. If we used 5 nearest neighbors, then we would say, okay, what are the 5 dots nearest to our red dot? And you can see it is 3 blue and 2 green. So we would classify this red dot as blue. So one of the decisions you make when you set up a k-nearest neighbors model is how many nearest neighbors do you consider? And this is really going to determine whether or not the boundaries of your groups are kind of very smoothed out, so a nice kind of straight line, or whether it's really going to have a lot of twists and turns around it, depending on if you have, so if you have a small number of k, then the boundaries of your classifications are going to be very wavy. As you get to more k, then it starts to smooth it out. And so the question is how clear do you want these classifications to be? How much are you going to allow for a little bit of variation? How much overlap are you allowing in those models? So let's take a look at the k-nearest neighbor. But just before we do that, k-nearest neighbors has the benefit of working with missing data, so it does allow for missing information. Many of these other ones do not. And when it comes to k-nearest neighbors, your predictor variables, those independent variables you're using to predict what the labels are, must be ordinal, interval, or ratio. So k-nearest neighbors does not work with nominal predictor variables. Now, because k-nearest neighbors considers, stop moving all over the place. Because it looks at what is nearest, it actually is a measurement of distance. And so we need to take into consideration the two variables, whatever is on the horizontal and one on the vertical, or however many variables you have, might be measured differently, right? So if we're thinking about age, then our average age, let's say, is 45, and we could look at the distribution from there. So there might be quite a range in the different ages. When we look at height, if that's what we put on the vertical here, there might be a lot more condensed. All the numbers are much closer together than the age. And so we need to recognize that because they are on different scales, we're going to need to standardize the data to make up for the fact that something could be much further away in age and not as far away in height. So we're making this adjustment here for the fact that the numbers are on different scales because this measurement of classification is based on distance. So we want it to equally consider age and height when it's building the model. Now, one of the uses of K-nearest neighbors is to design recommendation systems. So in a later video, we're actually going to use KNN to identify what products we recommend that you might like. And so we'll look at applications of this after we go through the different classification models. All right, so let's actually do some K-nearest neighbors. And we are working through the classification workbook. You can find that at drstephpowers.github.io/BIA. And we are here in Chapter 8 of the Business Intelligence and Analytics Handbook. And so if you click here where it says classification, it will take you to GitHub. You can then open in Google Colab. Remember, you'll need to log into your Google Drive, save a copy to your account. That way you are able to work through the workbook with us. We are going to be working through some different data sets. One is called bargain numeric, one is called CRM clean, and one is an attribute data set that we'll use with our naive Bayes. You can find them here. If you've been working through our previous videos, you probably already have them because the bargaining numeric is the coded version of our collective bargaining survey as we surveyed our union members. We prepped for bargaining. And our CRM clean was our customer relationship management database that we were looking at in our inferential statistics, descriptive statistics, and data visualization videos. So those are the same ones we've been working through. We're simply adding one more as we look at the naive Bayes classification method. But for KNN, we'll start by looking at our bargaining numeric spreadsheet. So to access that, you'll need to import pandas as PD and numpy as NP. You will need to connect your Python notebook to your Google Drive, and you'll need to take your Excel files and put them in your Google Drive. So then you need to tell it where to go get them. We're using this technique so that when you go to do this for your own data sets, you know how to put your data set into your Google Drive, and then you can simply call it up. So here these data sets, they are located in a folder on my drive called BIBA Handbook, and then they're located in a folder inside that called Chapter 4. So up to this point, to the slash after my drive, yours can be exactly the same. And then this last part here is simply to specify where it's located in your Google Drive. And then these are Excel files, so we're reading Excel. If you were doing a CSV file, you would change this to CSV, and you, of course, would change the extension to CSV. With the CRM clean file, we are actually just pulling information from one tab, one sheet in that document. There are two, and so we actually just need to specify which sheet has the information. If it has multiple tabs or sheets in your Excel file and you don't specify what sheet it's to come from, it will give you an error. It doesn't know what to do. All right, so we load those in. And we're going to start with K-nearest neighbors, and we're going to start with some ordinal data. So let's go back to our bargaining survey, and we're looking at question 15, 18, and 23. So just to remind ourselves, let's look at question 15. 15 was how satisfied were you with the location where you work? So that's 15, looking at satisfaction with location. 18, do we think that our workplace is safe? And then 23, what campus are we located at? North, south, and east. And so what we want to do is we have our labeled data here as to which campus they are associated with, north, south, and east. So the question is, can we predict what campus they are located with based on how they feel about the safety of their workplace and how they feel in terms of the satisfaction with their work location? Perhaps there's been some grumbling about one particular location. The building is a lot more run down. We think it's not as safe for people, and we think the people who work there are not as happy to be at that location. So we want to see if we can use how satisfied they are with their location and how safe they feel in their location to predict their location. Okay, so our labels are north, south, east, And our questions 18 and 15, notice, are Likert scale. It's ordinal data. So we are going to do a classification model with ordinal data. Now, just to take a look at it graphically first, we can use Seaborn and import scatterplot. We're going to use lots of scatterplots when we do classification models, cluster analysis, regression, forecasting, lots of scatterplots. So right now we're using Seaborn. We're going to import scatterplot. We're going to import here matplotlib.pyplot as PLT, and we've done that line before. We're also going to import what's called matplotlib just as MPL, so without the pyplot. And the benefit of doing this second import is that we're going to actually be able to change the dot size on our scatter plot, make it bigger so it pops a bit more. Okay, scatter plots are really made for lots of data points, and so the dots tend to be a little smaller. Here we have less data points, so let's make them big and stand out. So we're going to use that MPL and then the command rcparams. We're going to change the parameters here, and really we're just changing the marker size. So you can leave this formatting here if you like the size these dots are, and you can just use that command just like that in the future. Then we're going to call scatterplot. On the x-axis, so here, what we're going to do is we're going to use question 15, which is how satisfied they are with their location. Okay, question y, or so on the y-axis, the vertical, we're going to use question 18, which is whether they feel their location is safe. Then what we're going to do is we're going to color code the scatter plot with the different labels. So hue equals, and here this is question 23 from our data frame 2. Okay, and then you can choose the colors that you want. We'll just use palette equals deep. You can look up for scatter plot other hues and palettes to see what color schemes that you might want to have. We're going to create a legend. That legend we are going to put to the right here. So this first number in this B box to anchor tells us that it is to the right, because the number is bigger than 1, to the right of the graph. And then the second one, you can have it, it's a little bit up here. You could just make it more in line. You could make it 0 and it would just put it right in line here. It's up to you. If you want to put it lower, make it below 1. It's really just shifting the top of this box up or down compared to the edge of the graph. And number of columns equals 1 because we can just put it all right below each other. Okay, we're going to put the x-axis is going to be called location, the y-axis is going to be called safety, and we can run that and create our graph. So the key here is to look at this and say, okay, are we seeing clear clusters? Are we seeing clear classifications? So we can see, for example, maybe low safety, low location is this orange group, that's the south location. And then is there kind of a group that's the green? Is there kind of a group that's the blue? It looks like there's a bit more overlap in the green and the blue here. Now, on these axes I have, you'll notice that it goes 1.5. We could change this. We can do plt.xticks, and we did create, we put numpy in here, right? Yep. So np.arrange. And so we could specify for these, if it really bugs you that there's these halves when safety and location are Likert scale and they can't be halves, we could do 1, 5 steps equal 1. Oh, sorry. Got to put that outside here. And pull that. Let's see. Can never remember it offhand. All right, let's go back to our previous, one of our previous codes, and we can pull what that is, right? You got to remember all these different formulas offhand. So if we just go and pull our previous notebook. Actually, let's do it this way. It's probably easier just to see it here. All right, let's go to our data visualization. pull our notebooks, find one that has, here we go. Gotta remember all these things. That's why it's good to have templates so that you can just keep going back to them. All right, so let's do this. blt.x tick. Right. X ticks with an S. All right. And NP range. We don't want to go to 25. We want to go from 1 to, and remember it's up to but not including, so let's make that 6. There we go. Steps equals 1. Let's see if that got it to go. All right, so now that's 1, 2, 3, 4, 5. That looks great. Let's do the same thing for Y. So we use a range 1 up to, not including 6, increments of 1. We've done that for both axes here so that it shows we can't really have halves. All right, so what we see when we plot ordinal data with the scatter plot, it's a little difficult to really see all that's going on here just because this can be multiple people, this can be multiple people, but because you can only choose 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, they're hidden as to how many people that is. But what matters here for our classification is we're looking for kind of these boundaries as to where it is cut off. So what we want to do is we want to build an algorithm that is going to identify location 2, location 3, location 1, based on safety and location satisfaction. All right, so how do we do that? We're going to find as we go through these classification models, they all have a very similar setup, which is first we're going to import the classification method. So from sklearn.neighbors, import kneighbors classifier. That's what we're using when we do our KNN method. And then the other thing is we're going to see how good of a model this is. So from sklearn.metrics, we're going to import accuracy underscore. And this is going to help us then assess how accurate the model was that we created. All right, when you do a classification model, you have to train it and then you have to test it. So when we do our training and testing, if we have a large data set, then we can randomly select data to be the test data and randomly select a portion to be the trained data. We're going to do that in later models. Right now, we have a very small sample set. We have just our survey questions here. And so let's assume we've withheld a couple of the responses. So we've withheld information on a couple people, and we're going to use that to test the model. So here, we're going to train it on question 15 and question 18. And in order to get it into the right format for our training data, we need to do this 2_numpy. See if it'll tell us here. Okay, so this will get it into the format that we need. And then we have our testing data. So our testing data is going to be that group we withheld. And so what we have is one person who gave a rating of 1 for question 15 and 1 for question 18. And we have a person who gave a rating of 3 for question 15 and 5 for question 18, 5 for question 15 and 3 for 18, and then a fourth person that was 4 for 15 and 5 for 18. Okay, so we have our predictor variables, which here are satisfaction with location and whether or not they feel and their rating on safety. And we have separated our data into training data and testing data. And we've loaded that into the system. Now what we're going to do is have it fit the classification model. So we give a name to it. We're calling the command kneighbors classifier, and we're going to specify 3 nearest neighbors. So because we see we have some overlap here, we want to go with the smaller number of neighbors to allow for it to kind of curve the group as necessary to say this is a group here and this is a group here. Okay, the higher the K, the more it's going to smooth out the edges when it says here's a class, and so on. All right, so let's fit this. So first we have it build the model, then we're going to fit the model, and you're going to fit the model on your training data. Okay, and then we have to specify what it is that we are predicting. So here we are predicting our question 23, and our question 23 is the coded version of our north, south, east. Okay. Once we have fit the model on that training data, then we want to predict values based on the predictors from the test group. So this is where we had question 15 and 18 for the respondents that we withheld. And we're going to say, okay, use this model that you've created here and predict the label for this test data. So if someone said 1 to question 15 and 1 to question 18, predict what their label is. Are they north, south, or east? And same thing, it's going to then take this person here who said 3 for 15 and 5 for 18, predict what their label is, north, south, east. Okay, so we'll generate those predictions. So what this says is the person who did 1 for question 15 and 1 for question 18, it's predicting that they're from the south location. And the person who said 3 for question 15, so very neutral here, but in terms of 18, they were quite satisfied with the workplace safety. It says that they are in location 3, the east location. In this case here, where they were very satisfied with their location they were working at, and they were neutral on the safety of the location, it's also predicting, it's predicting here that they are at the north location. And if they were highly satisfied with both the location they work at and the safety, it's predicting that they are at the east location. So it's predicting 2, 3, 1, 3 for these 4 individuals we withheld. If the actual information is that the first person was from the south location and the second person was from the east location, the third was from the east location, and the fourth was from the east location, so our actual labels are this here, then when we go to see how well the model works, you can see it was off on 1 of the 4, so the accuracy here is 75%. So we can calculate the accuracy using that accuracy underscore, and you do y test and y predict. So you have what the actual labels are for the withheld data versus the labels it predicted. And we get an accuracy of 75%. Okay. The bigger the training data set, the more variability, the more accurate the model will be able to do in terms the more accurate it is. Now, when it comes to KNN, we can also use this when we have predictor variables that are interval or ratio as opposed to ordinal. So we could use the customer relationship management data set. And again, we could use the same process as before. And here we can plot on our scatter plot this information. So we're using scatter plot from Seaborn. It's all the same code. Import matplotlib as MPL. You already did that. You don't technically have to do it again, but just in case you're coming back and just pulling this set of code for your own data set, we have it all together. We're using matplotlib.pyplot as PLT to create the graph, and we created that MPL so that we could do this formatting to make the dots bigger. Okay, we're doing a scatter plot. What's on the x-axis? Here, we are going to be looking at questions 7 and 8 in the customer relationship management data set. So let's go back to that customer relationship data set and look at 7 and 8. So 7 was the percentage of listening per minute that our salespeople do, and 8 was the talking speed, words per minute. So can we predict what salesperson we're looking at based on how much they listen and how fast they talk? Can you identify the salespeople? So that's the classification model we're building here. is we are going to, on the x-axis, put the percentage of listening. And here on the left, we're going to do the talking speed. And then our hue here is going to be the labels. And here our labels are coming from question 1, which is the salesperson. And again, you can choose what color scheme you want by changing that palette. We are putting the legend to the right. Remember, this 1.15 says it's to the right. If it's more than 1, it's shifting it to the right. How far right is how much more than 1 this is. And then this 105, it's technically, I have it a little bit higher than the top of the graph. If you make it 1, it's lined up right here. If you make it less than 1, it's shifted down. 1 column, because we can just put it one right after the other in this. So this is just formatting. X label is listen here, Y label is talk speed, and we can then create this graph so that we can take a look. Now, we said that K nearest neighbors works well when there's overlap between our labels. This one has a lot of overlap in labels, okay? And so what we're going to do is try to create a model that's going to identify, looks like this is Chen and this is Garcia, but these others seem to kind of blur quite a bit. Zhao right here in the middle. And so we're trying to create a model to be able to identify the salesperson based on talking speed and the percentage of listening. Here, these are both ratio. If it's 0, they didn't listen, they didn't talk. And so we can have increments in between. Now, because these are interval or ratio, and they have different measurements, talking speed is measured differently than listening percentage, and K nearest neighbors is all about distance, we need to standardize. We didn't have to standardize in the previous example because they had the same scale. When they're ordinal and it's the same Likert 5-point scale, we didn't have to do any standardization. But when we have interval data or ratio data, then we do need to add in a standardization process. So we're going to add in one more package here, which is we're going to do StandardScalar from sklearn.preprocessing. So you're going to need your kneighbors classifier from sklearn.neighbors. You're going to need your sklearn.preprocessing, then the command is StandardScalar, and then you're going to need your accuracy score from sklearn.metrics. So first we import the necessary packages, then we specify our training data and our testing data. As we're going to see in some future examples, you can have it randomly select the training and the testing. Right now in our very simplistic examples, we're just going to set aside a group, and so we're entering in specifically, here's the test data, and then everything in the data set itself is the training data. So we're going to say xtrain equals, and then pull from data frame 3, question 7 and question 8. Remember, we need to convert it so it's in the appropriate format for this model. And then here's our testing data. So for our testing data, there is a person's information we withheld who answered 22 to question 7 and 48 to question 8. So one salesperson customer interaction was 22% for listening and was 48 for words per minute. A second person, 36 and 41, a third person, 46 and 42, and a fifth person, 58 and 46. So we withheld these couple data points in order to test it. In order to build the model, we're going to first do scalar equals StandardScalar and then parentheses. We're going to standardize our data because we have different measurement scales for our 2 different predictor variables. And so we're going to do xtrain scalar.fit transform. Okay, so this is going to standardize the training data. And then we're going to do scalar.transform xtest to standardize the testing data. So this line of code here, you want to keep that as is. And then all you're going to do is change what's the training data and what's the testing data. And you can just keep this code as it is when you go to use it on your own. So it's to standardize the data. Then we're going to do K nearest neighbors classifier. And we can specify the number of neighbors. So here we'll try 7, and then we'll go back and change it to a different number in a moment to see if it changes anything. All right, so KNN equals K neighbors classifier. We'll go with 7. All right. Then we're going to fit our K nearest neighbors with our data frame 3 question 1. So we're going to use our predictor variables. That's the X train that's already been standardized. And then we're going to have our labels, which is going to be our salespeople. So we're going to fit the model on our data. All right, why are you unhappy? Make sure I ran all this because I probably forgot to run something. I probably forgot to tell it what the training data was. It's complaining because if I forgot to select that, then the number of the information doesn't match in terms of number of data points on either end. Once we have fit that, then what we can do is we can then have that model predict what is going to be the label, so which salesperson, based on our testing data. So remember, we withheld this information here. Here's the listening percentage and the talking speed for 4 different interactions. And if we put that in X test, then it's going to predict who those individuals are. So it's predicting that the first salesperson, so this is the one that had did a lot of talking and not a lot of listening, then that person is Taylor, and it's predicting the second person is Zhao, the third is Debbie, and the fourth is Garcia. So we can see here that fourth individual has a very high listening rate, and so they're predicting Garcia. So let's just take a look. High listening rate, you can see why Garcia was predicted because that's up here. If we look at some of the other ones, let's see, what was that first one? Taylor had a low listening rate. Let's see. Low listening rate, and it's predicting Taylor. So I think there's a high talking speed. Yeah, high talking speed of 48. So you can see why it's predicting Taylor for that first data point. We withheld just 4, so when we then try to calculate the accuracy, we need to provide what the actual information was. Okay, so we need to have the labels that are from the test data. And then what we see here is that the accuracy here was 0.5. Okay, so it's the actual data said that that person who had not a lot of listening and very fast talking speed was actually Smith and not Taylor, so that one was incorrect. The Garcia one was correct, the Zhao one was correct, but the Debbie was actually Mensa, so that third one was incorrect. So it's saying 4642, 4642, and so it predicted that it would be Debbie, and it was actually Mensa. Okay, so we can actually change the model a bit. Perhaps we don't want to use 7 nearest neighbors. We could use, let's say, 3 instead. So we're shrinking the circle. If we go back to our imaging here. So we're switching from, say, a circle that's incorporating 7. That is going to have much smoother lines that are going to separate out the different groups. And then 3 is going to allow for a bit more waving. So let's see if we change that to 3, if it changes the performance. So we've already imported our packages. We don't need to do that again. Just to make sure we have completely integrated everything, we'll enter our training, we'll enter our testing, we'll standardize, we'll create a new model with 3 nearest neighbors. We're going to fit that model, and then we will have it predict. And here we get Taylor, Zhao, Smith, and Garcia. So you can see that it has now changed that third one to Smith. It doesn't match the information that we have, so our accuracy here is still 50% for this particular model, but you can see it has now changed to Smith. So let's actually go back and look. 46, 42. 46 and 42. And so it's now taking into consideration these blue ones here as we're looking at this location that is 4642. So how big your circle is or how small your circle is going to change what you're classified as. And so you have to choose then which, how much you want to, how many Ks you want in your nearest neighbor. Let's go back here. Okay. Now we can change the K, right? 3, 7, and so on. To give you an example of how this works, we're going to go away from that data set that we were looking at and look at a bit more generic one. So this here is just a bunch of packages that is going to be used to generate a data set. I'm just going to scroll to the bottom here. It's a lot of code, but it's because it's trying to create this. So what I want to show you here is that we have two groups here, the red group and the blue group. Notice that in this first scenario, the red's kind of on the top, the blue is kind of here on the bottom. In the middle group, they're quite mixed. And then in the bottom one, we have the blue on the left and the red on the right. So what all this code we're about to run is going to create is this information here to show you in these different situations, depending on how the labels are in terms of how the data is laid out, impacts which models might be better. So we're going to look at a scenario where we have the 3 nearest neighbors, and then let's go big difference, 15 nearest neighbors and 55 nearest neighbors. Okay, so quite a big circle in terms of consideration. So I'm going to come back to that in a minute, but the code here, you have it. You don't need to tweak it any. It's going to use our graphing, our matplotlib. It's going to use matplotlib.colors to help specify colors for the graph. And then it's actually just taking set data sets from sklearn that makes the circles and makes the information. And then it is using a bunch of, here's the standardization piece, and then using pipeline. We'll come back to pipeline later in later videos. But you can really just import all those packages. And then here, what it's doing is generating the data, and then it is doing the classification process. We have 3, 15, and 5, so the classifiers are here. So if you wanted to try a different number of Ks, you would change these numbers right here, and then these are just the labels that tell you which one they are on the graph. The rest of it you can leave alone, and it's simply to create the data with some noise and have that distribution. And so we'll just leave all of that as is. And this is so we can see here how this would work. So notice with the 3K, then there is a lot more movement. So if we look at this boundary, so like here's this kind of peachy color that's separating the red and the blue. Notice that it is not as, here's a straight line essentially. This allows for more waving, more moving around. So we can almost capture the actual boundary of the red and blue colors. You can see here, it fits pretty well in terms of that first data set. So this one is with less, a lower number of K. You can see here when we switch to a really large number of K, or maybe you can't because my face is covering it up. But when we have a large number of K, we're now looking at a very big circle. And so basically good 2/3 of the map here is just going to be labeled as blue, right? Because as soon as that circle gets really wide, it's capturing blue. So that bottom right one, you can see that most of that graph is labeling as blue, which means it does not do well with this middle scenario where there's lots of overlap. Okay, it's just labeling everything as blue, even though we see all these red dots here. Now, if you have some separation here, like in this first scenario, it doesn't do too bad of a job at separating out the red and blue, but definitely with the overlap, the higher number of Ks does not work well. So if you have a lot of overlap in your data, you want to go with a lower number of Ks as opposed to a higher number. The general rule of thumb for choosing K is that K should always be an odd number, and that way there's something to break the tie. So if we go back to say here, you can see when there are 3, then it's always going to push towards one color instead of the other. And here we have 5, it's pushing to one color over the other. So choose an odd number for K. And then when you're choosing K, if you surveyed, for example, 100 people, then an appropriate K would be the square root of 100. So let's say 10. Now that's not universally used, but when you're trying to figure out what might be an appropriate K, you can take your sample size, your 100 people, take the square root of it to get a K. And then adjust from there, adjust it down if you have a lot of overlap. Or you can leave it where that is. Now, whenever you're choosing a model, and we're doing the classification model here, what we want to do is we want to make sure that whatever we're choosing as the variables, and so in our previous examples here, we had listening speed and talking speed, we really want to make sure those are actually variables that relate to or associated with the labels of salespeople. So this is where we could go back to the one-way ANOVA that we did in our inferential statistics and look for statistically significant variables. So we're looking for ones where there actually is a relationship. Otherwise, no matter what K you pick, your accuracy is not going to be very high. So same thing with our even previous example, which is if there really is, if the safety of the location, people's opinion about the safety of the location and their preferences about the location really aren't related to the location, well, that one, it seems like obvious they should be, then it's not good variables. So we can use our inferential statistics and our data visualizations to make sure there is a relationship before we build our classification model.